GATE 2014 set 2 EC question number 30. A series RLC circuit is operated at a frequency different from its resonant frequency. The operating frequency is such that current leads the supply voltage. The magnitude of current is half the value of the resonance. If value of RLC are 1, 1 and 1, the operating angular frequency omega is being asked. For reference, you can refer to lecture number 19, second order RLC circuit, natural response, series and parallel RLC circuits of the NPTEL course Basic Electrical Circuits by Professor Nagendra Krishnapura, Department of Electronic and Communication, IIT Madras, and the YouTube lecture link is given here. The useful data that will be needed to solve this problem is that the impedance offered by the inductor is XL, which is omega L in magnitude, and the capacitor offers a impedance of 1 by omega C, where C is the value of the capacitor. In magnitude it is 1 by omega C, and if you see the impedance triangle, then R is real, so like this, and the inductor offers XL impedance in the plus J direction and the capacitor in the minus J direction. So the net impedance Z will be R plus J omega L minus J by omega C, or even it can be other way around. So the magnitude of the impedance can be written like R square plus this difference whole square and root over. So now we have written like this, Vt by Z is I. So now if you see, for omega L equal to 1 by omega C, this circuit becomes completely resistive for this value of omega, and the value will be maximum for the current because this denominator term becomes minimized. So now this omega is known as the resonant frequency. So as you can see, IT varies with omega, and for omega equal to omega resonance, this omega L equal to 1 by omega C, hence the IT value is maximum, and this part omega is less and this part omega is more. So if omega is more, omega L value will be more, so omega L will dominate omega C, so the circuit will be inductive, that is inductive dominant, that is the current will lag the voltage. And in this part omega is small, so omega L is less than omega C, 1 by omega C, because omega is small, so capacitive dominant, hence the current in this part, if operating point is at this part somewhere like this omega, then current leads voltage, which is exactly the same case in our problem. The current is leading the supply voltage, which means leading nature, so it is capacitive dominant, which means omega is less than omega resonance. So omega operating is less than omega resonance. Now coming to the solution, at omega equal to omega operating, the current value V by mod Z equal to V by 2R, where V by R is the I resonance, which is maximum value, and half of that, so V by 2R, and this condition is given in the problem. So now V by Z mod Z can be written as, this can be simplified as mod Z equal to 2R, where mod Z can be written as R square plus omega operating into L minus 1 by omega operating into C whole square whole root over equal to 2R. R equal to 1, L equal to 1, C equal to 1, so 1 plus omega operating minus 1 by omega operating whole square whole root over equal to 2, and squaring both sides we get omega operating minus 1 by omega operating whole square equal to 3, or omega operating square plus 1 by omega operating square equal to 5. So this will come down to omega operating whole to the power 4 minus 5 omega operating whole square plus 1 equal to 0. So now this can be written as omega operating whole square minus 5 omega operating square plus 1 equal to 0. Let omega operating square be a variable, then omega operating square value is coming out as 4.79 and 0.208. So from this, omega operating value is, neglecting the negative values, omega operating value is 2.18 or 0.45. Now 1 by root LC equal to omega resonance equal to 1. Now given that omega operating is less than omega resonance, since it is leading, so this is the actual frequency and this is not the operating frequency. So 0.45 radians per second is the operating frequency. So the angular frequency is 0.45 radians per second.